Okay, this is one of the most important slides conceptually to get. Let me explain it. This is done by Andrea Carusi in Italy. Very, very good work on his part, and it's an essential point. This vertical line is 2036, and it's the impact. In other words, if you're looking at the question of impact and possibility, what you want to do is look at an impact and then back up and say, what do I need to know when, et cetera, et cetera. But that's the way you do it. So here we have an impact in 2036, and the question is, how much delta V, how much change in the velocity of the asteroid do we have to apply to it at what date in order to cause it to miss the Earth? So we're talking deflection here. And you'll see here coming back between 2036 and, in fact, 2029, the close approach, it takes something like 1/10 of a meter per second, about 10 centimeters per second, that you would have to change the velocity of this 320 meter diameter asteroid, something close to 10 to the 11th kilograms, okay, in order to cause it to miss the Earth over here in 2036. However, because of that close approach, it drops down 5 orders of magnitude if you deflect it before 2029. Okay, that's great news. The corollary bad news, you know, it's always there, right? The corollary bad news, along with that good news that it takes very little to deflect it if you do it before 2029, is that you have to know its position very, very precisely. In fact, several orders of magnitude more precisely than you would have to know were there not a close encounter before the impact. The other conceptually easy way to understand this is in this range, you're having to change its velocity to miss the Earth. Here, you're having to change its velocity to miss a keyhole, which is only 600 meters across, instead of what? 2 times 6,400 kilometers across. So that's the challenge. Well, number one, it takes very little to deflect it, but before 2029, the bad news, you got to know where the hell it is. Okay, I'm going to go on to the consequences. Let's go to the other side of the equation. This is an excerpt from the current JPL table for impact risk on MN 2004 or MN4. And I'm not going to spend a lot of time on this, but what I want to do is point out in the public domain is all this information about the probability of impact of this asteroid, what date and time it's going to impact if it does, the distance above or below the center of the Earth, the width of the 3 sigma ellipse, etc., etc. All that data is in the public domain, and it's this data which I've used. However, JPL does not show you what that data means. They give you the data, but what I want to do is show you what it means. Now here is all these different parameters put together in a diagram, this obviously being the Earth. Here is that line of variations, that ellipse, okay, but it's almost a line. In fact, the width here is 51 kilometers, 3 sigma. We know today, if it hits in 2036, it's going to hit along that line. It's a very narrow ellipse, okay? It's very long. From time to time, it can get as long as all the way around the sun, okay? But it's very narrow. Okay, so, and here's the distance that you see here. So now what I'm going to show you is because you know the date and the time, and not just things like distance, you can do this. You can make that globe real, not just a blue blob. Now, don't pay attention to that. That's the only thing I could get off the web. Here's the real case for 2036. There is the path of risk for the 2036 potential impact. Again, 1 in 10,000 chance that it would hit somewhere along that line. But if it hits the Earth in 2036, it will be along that corridor provided I've done the math right. Okay? So let's get it checked. Okay? Now, let me tell you that you can see there that the most likely consequence, although not the only one, is that it hits in the Pacific Ocean. These are the angles which it will come in at if it's on the centroid or 45 degrees or 90 degrees, and it actually wraps around the edge of the Earth a little bit. So the question is, what happens if we get an impact out there? So I said to a friend of mine, Steve Ward, University of California, Santa Cruz, expert on modeling tsunami effects, let's drop that asteroid in the ocean there and see what happens. Here comes the event. There's the tsunami. And there are the final run-up wave heights which would occur if we had that tsunami event 1,100 miles, 1,100 kilometers off the coast there. It could be closer if it were further to the right. It could be further away and closer to Japan. But basically, those are the kind of wave heights. And let me point out that these wave heights all along the California coast are about the same as Banda Aceh in the Indian Ocean. In other words, you take the highest point anywhere in the Indian Ocean tsunami, you've got it all up and down the California coast, and even Seattle and up in areas like that, even as far away as Japan, you've got things that look like Madagascar. There have also been a number of models done on the cost of a tsunami. And if you take, I'm just going to do it right here, you go up at about 400 meters, you go across 4 million people on a global average, not that particular one, but on a global average anywhere in the oceans of the world, you're going to have about 4 million people affected. If you look at all kinds of statistics from World Bank, etc., and for a tsunami, you're basically talking about infrastructure loss, not loss of life, because you do have some warning. There will be lives lost, as there were in the Indian Ocean, but there was no warning there. You would have warning here. On a worldwide basis, the cost of infrastructure on a per-person basis, about $100,000. Therefore, the cost of that tsunami on a worldwide basis, $400 billion. If you take California's infrastructure costs, go up by a factor of 10 at least. Okay, $400 billion cost, okay, for 1 in 10,000 probability of impact. Okay, the resolution. Okay, let me just go on here to say that what we need to look at here is, obviously the resolution is to deflect the thing, but the question is, when do we have to make that decision? First of all, we want to complete the deflection by something like 2028. Okay, that means you might want to start the deflection maneuver because it takes some time, around 2026. You make a guess, 2023 to get there with the rendezvous, surveying the thing, docking with it, or if you want to do something else, impacting with it. Doesn't matter what the deflection technique is, it's going to take some time. I figure something like 2022 you're going to have to launch. To do a launch in 2022, you're probably going to have to decide to design and do this thing in about 2014. Now, you can put your own numbers in there, but somewhere around 2014, maybe 2016 if you want to take a chance, you got to make a decision. The question is, what kind of information do we have to make that decision?